a rod of constant length. We have a spring. And this is going to complicate matters for us quite a lot, and you'll see why. So the first thing we need to establish is, well, we say that the unstretched length of the pendulum is going to be L, and it is going to have a stiffness of K. So what is going to happen with this is that once we release it, the spring itself is just going to stretch, and then the mass is just going to swing. So we're going to assume that there is some kind of frame in the middle that prevents this from basically bending like this. So basically we're going to neglect any effect of bending. We're going to assume that the mass is not too large to actually have any effect on the bending of the spring. So it's just going to keep straight the whole time. But what happens is you're going to have this moving back and forth. So this is going to be oscillating at some rate. And then the pendulum itself is going to be oscillating at another rate. So we no longer have just one type of motion, which would be rotational motion about the pivot point. We now have a radial motion that is about the radial axis running along this spring mass system. So we could try using Newton's method. So one way we could do that is we could pretty much just draw a full free body diagram, and they just take the sum of the torques about the pivot point, and then use concepts such as the tangential acceleration, relate that to the length plus some displacement r, and then here in this case r is going to be some radial displacement, and it is actually going to be a function of time. So it is a function of time as well. So this is not going to be a constant value, but it's rather going to change with time as well. So that's going to make things a lot more complicated for us to analyze. Now you could try this approach and then you would get some equations, but the problem you're going to run to is that those equations won't be correct. And the reason is that if you do it like this by taking some of the moments, you're not really taking into account the fact that there is a spring force involved here. So the actual effect of the spring itself won't be taken into account, and the equation you get won't really describe the whole system, because remember, we now have a new type of variable here. So if you get just one equation of motion, that's not enough. You need two equations of motion that relate. Each equation of motion will encapsulate the motion of one of the variables. So we have two variables, we need two equations of motion. So the next thing you could do is you could easily try and zero the mass, and then you could have something like this. So you would have the restoring force times whatever displacement r you have, and then you're gonna have mg going in this way, and then you're gonna have your angle, and then your force mat, and so on and so on. So you could apply some of the forces in x and y directions to derive a new equation of motion. Now what I want to do is I want to approach this problem from the perspective of Lagrangian mechanics, and the reason for that is that it can get quite confusing when you use Newton's method in this case, because of the fact that this thing is just going to be changing in length the whole time. So what we're going to do instead is we're going to transform the problem into polar coordinates. So we're going to have the radius, so we have some radius, but the radius is in here is just a radial displacement. So remember, we start off with some unstretched length of the spring, and then the displacement about that unstretched length, that equilibrium kind of length, is going to be given by this variable r, which is a function of time. So using polar coordinate transformation, our radius, our full radius, is now going to be that constant plus r times sine theta for the x direction, and then for the y direction we're going to have L plus r cosine of theta because of the projection here. Now I have done the derivation beforehand because this is a really long problem and it would have taken forever to explain if I had just written down everything on the board. So what I'm going to do is try to explain each step individually so we can focus on one step at a time, and then hopefully that will give you a better idea of what is going on. So first of all, let's focus on this part right here. So you're gonna differentiate this variable here and then this variable here, and the reason is that, you know, for your kinetic energy you need the velocity terms. So velocity terms are going to be the first derivatives of these two variables. So for x, what you're gonna do is, well, first of all, expand this out, and what you're going to do is you're going to get the following. You're gonna have the derivative of this with respect to time. Well, you're gonna have to differentiate the function outside and then multiply that by the derivative of the inside, which is theta dot, and this is the angular velocity. The next term is in line is going to be r times sine theta. So what you notice is that you have, well, you have two functions of time. R is a variable with respect to time. Theta also changes with respect to time, so you're going to have to apply the product rule. So the first thing you do, you differentiate this one with respect to time. That gives you r dot times the other function. And then you're going to multiply this, leave it unchanged, by the derivative of this with respect to time, which is going to be this after applying the chain rule of differentiation. And then you apply the exact same method to y. So basically you're going to have some negative terms here because cosine differentiates into minus sine of theta. But the idea is that these are the equations that you're going to be working with. Now, obviously, for the kinetic energy part, you're going to have to square the velocity terms because that's how they appear in the equation. So essentially, you have to take this whole thing and you have to square it. So you're going to have to do the same for each one. That's going to be quite a long process. You have 3 terms, you square that, then you're going to get 9 terms in the end. Of course, you will see that things simplify quite a lot once we add the terms that are common. So there are some repeated terms here. So basically you're going to multiply this by itself, gives you this, then this by that, and so on. So this derivation is something I recommend you do just for practice in terms of the skills of handling the algebraic expressions. And now we could perform some simplifications. So for example, let's say that I grab this expression right here and then this expression right here. We know that those two are the same, so we could add them up and then just have 2L to reduce the number of terms in this sum. Now what else are we gonna have? Well, we're gonna have this term here. So let me just do it in a different color just so that you can see what is going on. So let's do purple for this one. We have this term here, this term here. We're going to add those two together, so that's going to become one single term. And then I believe we also have this term repeated here, so let's do that in a different color as well. So we're going to grab these two here. And then basically those 6 terms are going to simplify into 3 terms, just simply by adding them up. But I'm not going to do that now, and you'll see why. So let's now do the same thing for y dot squared, and I probably should make this dot a little bit larger so you can see that it is the first derivative. And we're gonna do the exact same thing. We're gonna expand it out. Sort of a tedious process, but you can get there very, very steadily if you work through each step without rushing too much. Remember, when we're dealing with classical mechanics and with complicated problems like this one, you want to really take your time, because if you make a mistake here now and then you spend all this time trying to derive the equation of motion, and then in the end you realize, oh, I made a mistake here, you wasted a lot of time doing that. So it's better to be very, very meticulous when it comes to deriving these whole expressions here. So okay, let's see what else we have. Well, it turns out that we're gonna have this expression here. So I believe it was somewhere here. Yes, this one here. So you'll notice that this one is exactly the same as this one, but now it has a negative sign. And then this expression appears here once again, and it also has a negative sign. So it turns out that these 4 expressions here are going to cancel out, because remember, the kinetic energy term is going to be this plus that times the mass. So when we add these two equations together, all these four terms are going to cancel each other out. Now let's see what else we have here. We have this term here. Well, if we notice, this is actually exactly the same as that one. And this one here is also the exact same. So that means that once we add these two equations together, this is going to cancel out with those two. Okay, so now probably should scratch them off a little bit. So we have eliminated essentially 8 terms already from this whole. Basically, it's just a mess what we have now, but we have eliminated a lot of terms, which is good. And now what else can we do? Well, we need to really look into the sort of things that we have here. So for example, there are certain things that we won't be able to get rid of, but we can make some simplifications. So for example, this here, added to that, we have sine squared theta plus cosine squared theta. This factors out, so basically this term and that term go away. So what we can do is we can say, well, let's eliminate this and that, and let's get rid of one of these, such that we know, because remember, when you are adding them, you're factoring this out, so you won't get 2 times r, you just get r dot squared. That's it. Okay, so you're gonna have that term. And now what else can we do? Well, we can simplify a few of the other ones. So for example, this term here, so we have this term here, and this, not this one, I believe I was looking at a different one somewhere here. Yes, this one right here. So basically notice that we have these two. So we have sine squared, so those two are going to become 1. And then if we look at the blue one, so we're going to have this cosine squared, so basically we're going to have this. So I should have done this in blue instead. Okay, so we have this plus that becomes 2 times L theta dot squared times r times cosine squared theta. This one becomes 2 times L theta dot squared times r times sine squared theta. If we add the two equations together, what happens is that we can factor out this whole thing. So basically we're gonna get the sine squared theta plus the cosine squared theta are going to become 1. So what we can do is we can easily get rid of these two equations, get rid of this term, and now we're gonna have 2 times L theta dot square r. Okay, and the last thing we want to do is we're going to grab this term here, this other term here. So you notice that you have common terms here, so you can factor this out. When you add them together, this is gonna go out with that, so let's eliminate one of them. We're left with that term. And then the very last, so you notice that there are a lot of things happening here, but we're trying to come to terms with the fact that we have to deal with a lot of terms added together, so we're just doing it step by step, seeing what we can eliminate. So here you have this term that is repeated here. You have a cosine squared theta plus a sine squared theta, so this is going to go away as well. Okay, so now that we did all this incredible mathematics here, now we're going to add this together. So basically we're going to have this term plus 2 times this term, which is right here. Then we're going to have this term here. And then the last one is going to be this one. And that's it. We're done. We're done with our total velocity kind of magnitude squared. And now the kinetic energy is just going to become half of the mass times x dot square plus y dot square. So we have this term here. Now for the potential energy, we're going to have two things involved. We have the gravitational potential energy, which is going to be given by the total distance from the mass to the reference point here, which is the pivot point. Now normally what we would do is we would take the entire length, the total maximum length of the thing, and then we would subtract it from the horizontal projection of this angle onto this line. and then this would be the height that we use for our potential energy. In this case, it is hard to tell what the maximum is going to be here, because remember that the radius is constantly changing. So what we're going to do is we're going to assume that this is going to be the total length. So basically we're just gonna take the potential as it is, but we're going to be looking at it from the point of view, from the perspective of the mass. So basically if we look at it this way, since we're pointing upwards, the potential energy for that in terms of the gravitational potential energy is going to be negative. So this part here is quite crucial because the sign actually matters. Because we're looking at it from bottom to top, that means that the potential is going to be negative. If we were looking at it from the top to the mass, then it would be positive. And now the spring is going to have this potential energy, so we know that the potential energy for a spring is simply going to be half of k times x squared. But in this case, I believe I made a typo here. It should actually be r squared, because remember that the displacement is given by that radial displacement r. So that's going to be the variable here. Now what we can do is we can write down the Lagrangian of this whole thing. So it's going to be kinetic energy minus potential energy. And now we're going to have a pretty massive equation, as you can see here. So you just add the terms together. Remember that we have a minus here, so this sign and this sign are going to change. And what you're going to get is a Lagrangian of 5 variables. It is a function of 5 variables. You have radial displacement, rate of radial displacement, then you have angular displacement, angular velocity, and time, which is contained within those 4 there. So as we discussed, because we have this set of variables, that essentially these two belong to the same kind of variable. This belongs to that, this belongs to that. We need 2 equations. So the first Euler-Lagrange equation we're going to derive is going to be based on the radial displacement. So we're going to take the whole Lagrangian, we're going to differentiate it with respect to the radial displacement, and we're going to get the following. We need to isolate the terms that contain some r in it. So for example, this term has an r, differentiate that, becomes just the constant attached to it. So when you expand this out, you're going to get this term here. The next thing that contains an r is this term here. So remember, r is a different variable from r dot. So this one is going to be m, so 2r times theta dot squared, but the 2 is going to cancel out here, so you have mr theta dot squared. And then on this side, well, you're going to have r here, so basically you differentiate, that becomes 1, so you have mg times cosine of theta. And finally you have r here, so that means that this comes down, the 2's cancel out, and you have minus kr. Now for the other element of the Euler-Lagrange equation of this variable, we have the velocity. So we basically differentiate the Lagrangian with respect to this radial velocity here. And we notice that there's only one term in the entire equation that is actually this variable. So what is happening is we're going to differentiate that. So this comes down, that becomes 2r dot. And then the 2 cancels out with the 2 here, so we have mr dot. And now we take the time derivative of this whole thing. So we're basically going to get m times r double dot. So now if we write the Euler-Lagrange equation, which is basically this term equals to this term, we get the following equation of motion. So this is going to be an equation of motion for the radial acceleration. But you notice that it does have terms that depend on the angular displacement and the angular velocity. So we're going to get a set of 2 coupled second order non-linear differential equations, which is really tough. We cannot even solve it analytically. So I'll show you later on how to solve this numerically. But for now, let's focus on the other set of equations, or the other equation, which is going to be given by these 2 variables. So if we go down here, what we're going to do is we're going to take the whole Lagrangian again, and now we get differentiated with respect to theta. So we notice that there's only one term of theta here, which is this one, but obviously this is multiplying this whole thing, so we need to take the whole thing here. So differentiate with theta, this becomes minus sign, so we have this term. That's it. Pretty straightforward. Now for the angular velocity one, it's a little bit more complicated because we have three terms here that are actually the angular velocity. So we're gonna basically differentiate each of them with respect to the angular velocity. So 2 comes down, pretty straightforward. Then cancel that 2 out with the 2 here, multiply by the mass, and you get this massive expression. And now you're gonna differentiate the whole thing with respect to time. So now we get even more complications because we have the radial displacement is also a function of time, so we need to differentiate that. So we're gonna have to apply product rule here and then the product rule here once again. So if you do that very diligently, you get the following equation here, and then you notice that you can rearrange terms by factoring out common terms. So basically you're gonna get this expression here and then plus this expression here. And once you have done all that, you can write down the Euler-Lagrange equation. So you have this equals to that. And then on the one side, what you're gonna get is, well, you notice that you can actually express this in terms of L plus R squared. And then you're going to have the following. You're gonna have the following equation. And if you divide everything by m times L plus R squared, you get the following equation of motion. So this one is going to be for the angular acceleration of the mass, but now you notice it is also dependent upon angular displacement and not angular displacement, radial displacement and radial velocity. So we have two equations of motion, both of them are nonlinear. So notice this one has a nonlinear term here, we have that, and also this one here, and this one has this nonlinear term here, and then also, well, this could be considered nonlinear because they're 1 over the variable, but you get the idea. You have two sets, or basically just two coupled nonlinear second order differential equations. So the dynamics of this system is actually really interesting if we analyze it through a computer and we develop a simulation for it. But for now, what we have worked out is the mathematics behind it, and we know that these two equations describe the whole motion of the system, both the mass in terms of the swinging and also the displacement due to the spring. So you can see that this was a fairly complicated problem, and obviously even though it was really tedious in terms of derivation, we know that it was fairly simple once we got to this point, because all we had to do was, well, we just take the difference between kinetic energy and potential energy to get the Lagrangian, and after that it just becomes a matter of differentiating things and then rearranging and doing some algebraic manipulation. But in general, the derivation step that takes the longest is probably getting the kinetic energy right, because we needed to perform this change of coordinates in order to approach the problem in a much better fashion. Otherwise, we would have had some kind of a lot more variables involved if we use the x and y kind of Cartesian coordinate system instead. So hopefully this gives you an idea of why the Lagrangian is important and why it allows us to analyze systems that the Newton's method may not actually be suitable for in some cases.